Well, thank you everyone for inviting us to be here today. And thank you especially to Carolyn for shepherding this process through. Bob and I have been climbing a steep learning curve on a lot of the issues here that many of you are very familiar with. So anyway, I know we have a diverse audience today and some very technical folks and some maybe less technical folks, but everybody has sort of the same interest right now, and that is to understand what some of the impacts of this proposed mining action will have on the town and downstream. So without more ado, I just wanted to again introduce Bob. He's on the line here from Colorado. His company is called Integrated Hydro Systems, and I'm from Tucson. So PARA commissioned the study with the primary purpose to evaluate potential impacts of South 32's proposed discharge of treated water from the Hermosa project to Harshaw Creek as described in the August 2020 ZIPDs and APP applications. This is just a little introduction for anyone who doesn't already know, which is probably no one here, but just to get everyone familiar with the site, there's Patagonia, and about 5 miles south is the Hermosa project. This is in the heart of the mining country in the Patagonia Mountains. They're targeting the Taylor deposit and the Clark deposit here. Both have different kinds of metals. And they propose to treat water from the dewatering activity to prepare for underground mining into Harshaw Creek, which is outlined here in blue. The initial dewatering rate is listed as being up to 45 gallons per minute, and that water will be treated and discharged to the creek. So PARA's motivating factors, as I understand it, Bob and I have talked about this. We understand that they were concerned because there's already a known risk of flooding in Harshaw Creek and in the town. And then South 32 presented to the town and the county in July, and their assessment was that there would be no surface water impact in Sonoyta Creek, or very little, from this discharge. And PARA is curious to examine that finding. This is a little background on some of the historic flooding in the town. I'm sure many of you will remember the October 1983 event that brought widespread flooding to most of southern Arizona. This is a picture right here from Highway 82 in town. This is the FEMA floodplain map for the town. You can see pretty extensive coverage outside of the channel of Sonoyta Creek. And this is a graphic from the 2017 Watershed Management Plan for Sonoyta Creek Watershed. And they do mention some perennial sections of many tributaries along Sonoyta Creek, so including parts of Harshaw and Temple Gulch and so on. So we know that flooding is a potential hazard here, even without any further action, just because of the nature of the watershed, being a lot of bedrock and shallow groundwater. Data up on top here, this is stream flow data provided by the Nature Conservancy. These are manual measurements made at the Patagonia Sonoyta Creek Preserve. And you can see in orange there's some areas that have kind of extensive periods of elevated base flows. And whenever this happens, that means that whatever little extra storage capacity there is in the system is probably minimal because what flows are coming out of the ground at higher levels than normal. And if we look at those, a couple of historic flow events that people have recorded and posted on YouTube, their favorite videos, you can see one was from August of 2016, and that followed a fairly large rain event. These are millimeters. This is satellite-based precipitation data here for the watershed. So not a huge event, 11 millimeters, half an inch, and then followed by another smaller storm on August 9th, and that produced a flood in Harshaw Creek that I'm going to try to show here. I'm going to have to try to share a different screen, so this is tricky. Bear with me just a moment. here. Can you see this?
Yep.
Okay, so this is just an example of a kind of typical monsoon rain event and following flood on Harshaw. And I think I will just go straight to the other one. Get there.
That it shouldn't be.
That
That
is not what I wanted to share.
If you are having a gathering in your
Aye,
home,
aye, aye.
that you should limit that gathering to no
You
more
should
than
limit
20
that.
people, provided your space is actually large enough to allow this.
I'm going to get out of that because I don't know how to
Between
stop
bubbles
YouTube
that's
from doing its
necessary for
thing.
20 people.
Okay. We'll go back. Knew that was going to be complicated through Zoom. I'll go back to my own screen here. Anyway, the point of all that was just to say that folks who live in the area have experienced pretty significant floods. The one in 2017 followed a series of small typical monsoon storms in July, and produced even a much larger flood, which I'm scared to even try to show now because of that last complication. But just saying that folks in the town know that typical monsoons can produce pretty exciting runoff. This was South 32's findings of their pollutant management area and discharge impact area along Harshaw Creek. Here's the Hermosa project. And this is in blue is the maximum extent of flow from the water treatment plant that they produced in their findings presented in July. And so we are interested in examining the assumptions and the methods for how this was determined, and exploring the use of another tool to examine that the same discharge in a different way. This is also from the South 32's July presentation. It's a little hard to see, but this is results of their simulations, computer simulations, and they find that this area in the light green hatcher is the area of simulated groundwater rise associated with that discharge into Harshaw Creek. They said a maximum of 20 feet, and this is about a 3-mile wide area. Down here in the darker green and pink, this is the area of mine dewatering drawdown that was simulated by South 32, with most of the concentrated area being around the mine footprint itself. For this project, we reviewed many documents, in particular, the 2 applications to Arizona Department of Environmental Quality for significant amendment to the Aquifer Protection Permit, and a ZIPD's permit application for the Hermosa project. We also reviewed about 30 other documents pertaining to the area and to the hydrogeology, and specifically related to this project. So this is just a close-up. This is out of the APP document. Here's the mine footprint, existing water treatment plant here on Alum Gulch. And then the second proposed treatment plant, WTP2, is here, and it would discharge to an unnamed tributary on Harshaw Creek, which then would flow down through Harshaw Creek. So our study objectives were to really just evaluate the effects of 4,500 gallons per minute of mine dewatering discharge from that second treatment plant on stream flow in Harshaw and Sonoyta Creek, on the conveyance of that discharge under the natural runoff rainfall event regime, plus the dewatering along Harshaw and through the town, and groundwater if impacts from dewatering in particular, and from flows in streams. So groundwater dependent ecosystems and aquifer storage changes. We also wanted to just assess the baseline hydrologic conditions, which hasn't really been done before, and what are the controlling factors on those conditions. And finally, we're interested in developing a robust numerical model of Sonoyta Creek watershed, which could be applied to other problems in the future. To do this, we started with a tool known as MIKESHE, and this is a fully integrated model. It's been around for about 50 years and it's widely used overseas in many parts of the world. Less well known in this country, but it's a very powerful and fully coupled integrated model. And what integrated modeling means is that the modeling system is driven by the top processes from the atmosphere downwards. So it starts with precipitation and evapotranspiration, which hits the ground and is then either routed as overland flow into and infiltrates into the unsaturated zone, or runs off into a channel, which then infiltrates into the groundwater system, or is directed to sewers, for example. And that groundwater flow is then modeled and it can be abstracted back to the surface if pressure is appropriate, or pulled up into the unsaturated zone by capillary forces, or can go right back into evapotranspiration. So all these systems are coupled together and they're running at the same time. The nice part about MIKESHE is it's very modular, so you can use the different modules independently and have your own temporal and spatial scales for each one. These time scales that can vary from days to years to even centuries in groundwater, for example, can be coupled with a surface water system that depends on processes on a seconds to hourly basis. You can choose which processes to include. You can choose simple or complex solutions. The groundwater part of this is virtually identical to ModFlow. And the surface water part is FEMA approved for flood risk analysis. I'm going to turn this slide over to Bob here. He's going to talk about the development of the MIKESHE model.
Sure. Hello. Can everybody hear?
Yes, sir. Great.
Yeah, this is just a basic flow chart describing how we pull in data from different sources. In the top and the darker blue boxes, we're getting data from various sources like the USGS databases, Arizona Department of Water. We're also collecting a lot of the climate data, which is hourly and distributed from another data source, and that's used to drive the model. We get remote sense data on soil types and distribution, vegetation types and distribution, and how that vegetation changes over the year, land use. And then we also collect whatever other kinds of data we can get our hands on, like stream discharge, water level data. And notably here, we are sort of limited on the data that goes into the model for calibration, but that'll be a point we'll come back to here. So that all goes into an initial model development. And then the next step in the sort of lighter blue box, we talk about this preliminary phase 1 model calibration. And we're really looking at a 20-year period. It's hourly. So we take every storm event that's distributed and we're modeling that. And we're trying to calibrate our model against the available data that we get. So in fact, some of the best data tends to be from the Nature Conservancy data set that they provided nicely. And then once that's calibrated, we can actually go into developing model scenarios where we actually then have a sense of comfort knowing that what we predict is related here to this WTP discharge has some sense of reality. There are boxes to the right that talk about a latter phase that gets into more detail of calibration. We're not covering that really in this part, but it's just shown as a typical flow chart of how we produce and develop these models in phases. And then on the last side is sort of a predictive uncertainty analysis, typical of doing models like this to try and account for the uncertainty that crops up in all of the input in these models.
Thanks, Bob. We'll go into the conceptual model development here. This is just a cartoon showing basically the idea behind modeling the Sonoyta Creek watershed and how much of it is dominated by bedrock, which you see here in this sort of gray brown. But there is a kind of a thin veneer of more permeable materials in the mountaintops down to the valleys. And then within the valleys, thicker alluvial deposits that include sands and gravels and some clays on top of a layer of weathered bedrock. And many of the wells, most productive wells are screened in this alluvial zone. Some of the small wells and many wells that weren't successful were screened or were drilled into the bedrock zone. MIKESHE has a very sophisticated unsaturated zone process. And really the important point here is to show that it can handle variations in soil types all the way down to the water table. And in this case, you see a clay layer here underneath the surface that is building up a saturated zone from recharged water from precipitation, or for example. So if water is manages to fall onto the earth and then infiltrate down into the soil, if it encounters this low permeable clay layer, it will not be able to pass through quickly, but it will actually pond up, creating a perch zone here. And that kind of dynamic is well captured in MIKESHE model. Over time, this water will dissipate gradually through, it'll infiltrate gradually through the clay and make its way down to the water table. So the important part here is that we can capture the dynamics of these varying layers of lithology. There are also different mechanisms for producing surface runoff in watersheds. The simplest is called Hortonian flow, and that's just like this. If this is the watershed surface and the groundwater zone is down here, very, very intense rain fall on the surface and exceed the soil's capacity to infiltrate that water. And so water just runs off everywhere. Another way is to have shallow bedrock underneath the surface. You see that here in this second panel underneath the surface. And in this case, any water flowing across the surface would be prevented from infiltrating by this shallow bedrock, and it would be driven on into a channel somewhere. The third way is with shallow groundwater. So if this is the surface and here is a shallow groundwater zone underneath the surface, any water falling on the surface would potentially infiltrate a small distance into the ground, but then it would hit this water table, which prevents any additional infiltration. So we call that rejecting infiltration. That water is rejected and forced to go on down to a channel. We really will be focusing on these mechanisms here today. The evidence for surface runoff mechanisms in this study, there's quite a bit, but we believe that much of it is controlled by shallow groundwater. Some other reasons we believe that it's not Hortonian flow is that the range of soil permeability that's reported, these aren't the kinds of soils that produce really peaky discharge. Aquifer storage effects are apparent in the discharge data that the Nature Conservancy provided us for the preserve. We know that there's, from well logs, we can see there's relatively shallow groundwater beneath the town in Sonoyta Creek. There's perennial flow along some of the lower reaches of many of the tributaries downstream of town where shallow bedrock forces the groundwater to the surface. So we're looking at this shallow groundwater and shallow bedrock as two forces that are creating surface runoff in this watershed. These are the Sonoyta Creek data and the precip data from the Patagonia Sonoyta Creek Preserve that Nature Conservancy provided. You can see here this green curve is annual precipitation from satellite data. Then the blue is precipitation reported from the preserve, and the red is stream flow measured at the preserve. And here you can see some areas where after a little peak flow, you see some delayed response in stream flows that are elevated over time. And this just shows that there's some capacity in the system to absorb and detain runoff and then release it a little while later. but it's not a whole lot. So the regional model set up in assumptions. Here you can see the boundaries of this watershed in pink. This is a Sonoyta Creek watershed here. This abuts another MIKESHE model that was done for the Cienega Creek watershed. This watershed, like most MIKESHE models, covers the entire watershed boundary. So all the way to the top of Mount Wrightson and all the way down to the confluence with the Santa Cruz River. The grid cells are 500 meters. It includes all the tributaries you see here in blue and the main stem of Sonoyta Creek, as well as Patagonia Lake. Climate data is acquired from satellites, as we mentioned. The National Land Data Acquisition System, or NLDAS, provides these very nice continuous data sets for these grid areas that are about 11 by 14 kilometers. So they're kind of large scale, but nonetheless, in lieu of other data in supplementing other local stations, this is an incredibly valuable data set for a model that depends on atmospheric inputs to really drive the hydrologic system and the snowmelt response. So here you can see the precipitation, potential ET, and hourly air temperature. These are critical inputs for MIKESHE. I'm going to hand this over to Bob again and let him walk through the next couple of slides. So go ahead, Bob.
Okay, thanks, Laurel. Yeah, this data set is just from the USDA's Sergio Soil Survey data set, and we process this in GIS and convert the soil textures like clays or silts or sands. Those variations relate to hydraulic properties in the soil. So of course, sands and gravels are much more permeable than a clay. All of that information is shown here. The lighter colors are more permeable, the darker colors are less. So the tendency with a higher intensity rainfall event, you would have more runoff in blue areas here. And so all of that information is converted into MIKESHE, and then we make assumptions about the depth and layering of the soil types below that. But this data set does drive our hydraulic properties as an initial estimate. Yeah, I guess, Laura, I don't know if you want to talk, but these, I think, go ahead.
These are just, these pink triangles along Harshaw Creek just represent locations where we found well logs from DWR's image records that show considerable clay in this system. And in this case, you know, down to 0 to 18 feet, we found clay mentioned in the well log. Here down to 30 feet, 2 to 30 feet clay. This one up here has black and brown clay all the way down to 80 feet below ground surface. So just some evidence that the impacts of clay in the subsurface could be quite significant along the system.
Hey, Laurel,
yeah.
Can I just add too that even though the surface of the stream bed in Harshaw might show fairly sandy, gravelly material, these logs really confirm that you don't have to go very deep before you start hitting these really low permeability clays.
Mm-hmm.
This is a couple of other anecdotal pieces of information. The picture on the left is from the South 32's APP application, I believe, and ERC did the analysis of the pollutant management area. They studied 5 locations on Harshaw Creek, and this one is kind of in the middle, but this one shows clearly mud cracks on the surface, and it's this kind of very fine material that just seals up like glass. When you rain on it, it soaks up. Once the clay silts wet up, they are basically impermeable. This is from a 1967 paper by Nassereddin, his master's thesis. He spent a lot of time characterizing the alluvial aquifer in the Patagonia area. And he found that in that top layer 1 out of 5 layers, that top layer had the most clay at 21% silt and clay. These borehole logs are also from the APP application. This is part of the geotechnical study that was done by South 32. And a lot of these borehole logs as well mentioned clay. And here is a 3D lithological model of the basin put together from the well logs that we have access to and borehole information. So you can see we're facing north west here. This is Mount Wrightson over here and Patagonia Lake, Santa Cruz River out here. Importantly, the key is provided here. So black is bedrock, clays. This is all subsurface, by the way. For those of you who haven't really seen a lithologic or a borehole log before, this is all projecting conditions in the subsurface over the land surface. It's also confusing. All this is underground material here. But the clays are in this sort of bright blue here. And then silts mostly along the top were found here in green. And then the bright yellow and orange are sands and gravel, so more permeable materials. So at first glance, you see that some important details, like a lot of clay in the Sonoyta Creek Sonoyta Creek drainage upstream of the town of Patagonia. A lot of shallow bedrock in the Harshaw Creek drainage here. Some clays near the surface, some sand and gravels here in the middle part. Considerable, very shallow bedrock south of the town of Patagonia, and pretty much clay, a lot of clay in the upper part of the watershed here. Not as much data out here. So these are just the borehole logs that we examined. There are many more, but there was sufficient evidence, we thought, to say that there's definitely a lot of low permeable soils on the surface and shallow bedrock to control surface runoff behavior. Just another perspective, looking from the upstream part of Sonoyta Creek down toward the town of Patagonia and farther down toward the lake. So in the MIKESHE model groundwater module, we conceptualized that model with 4 model layers. The largest is a competent bedrock layer underneath everything that where people are concerned with producing groundwater. That happens much higher up. But so that's modeled with almost 800 meters of thickness. The top 10 meters or 30 feet on the mountaintops and down the slopes is that weathered bedrock layer and a little bit of alluvium, and then in the valleys, thicker alluvium.
Laurel, can
Yes.
I add another point? The competent bedrock here is an initial assumption. We are aware that there are the geology is more complex there. So, but this is we didn't have that information available with depth, but just thought I'd point that out, that we're aware of that.
Thank you. Actually, Bob, why don't you keep going on this next one?
Sure. This is just a map that we produced for the input into MIKESHE that estimates the material above the bedrock, the weathered bedrock, to ground surface. So it shows a map of the thickness, or an isopac map in feet.
Let's stop.
I'm sorry? Did somebody say something? Yep.
I've muted him.
Okay. But the brighter colors here are the reddish colors, mean that the thickness of what we call the unconsolidated material, or the soil, it's loose, it's not rock, is hundreds of feet, whereas the blue colors are more in the 10s to 20 feet. And we've made some assumptions, but you can see that our assumptions are trying to take available data. So all the purple triangles are the boreholes that Laurel showed on the cross-section maps that we made before. And we've also overlapped that with red squares that have numbers showing the depth in feet to bedrock from a regional study. And you can see there are 3 dots with kind of within the northern part, but also dots in the basin to the south and east. And these are the interpolation, just using those dots, are the green lines. We found, rather than relying on that the local data provides better constraint. So we use that data, but we supplemented it with the information from the purple triangles. We've also made an assumption here that in the drainages, you'll see they're lighter colored than the areas in between drainages, say like to the north of Sonoyta Creek. On the drainages there, you can see darker blue and lighter blues in the drainage areas. And that just simply means that we're assuming less soil covering over the bedrock and non-tributary areas, and a little bit more soil in the drainages. It's an initial assumption without data yet available, but we also, just to make a clear point, all the purple triangles, there are more boreholes available. We just did this as an initial cut, kind of in the focus area. For the groundwater part of the model, we utilize 2 sets of data. We have to provide a sense of how easily water flows through the rock, or what we call the hydraulic conductivity, and then also how much water the aquifer material stores within it. And so we took as an initial cut information from mining modeling for the Rosemont area, the watershed to the north that's well published and available. And then we also helped refine that distribution of those properties, at least at an initial model level here, with the Arizona Geologic Survey superficial geologic zones shown here. And then you can see that, like in the red areas, that's an andesite. The purple areas are granodiorite. The light green is conglomerate. Again, we realize that around the mine area, we don't have the variation in that geology with depth that was apparent in some of the presentation pictures. But this is a first cut model intended to kind of look at how to set this up and get initial estimates of what happens to the discharge water. Oh, one more. We spent a bit of time because we found in other basins in Arizona where we've applied MIKESHE that faults play a pretty important role. And so we made, just as a first cut, we went through a number of available documents and pulled off various mapped faults. So there's the Santa Rita fault scar that goes into the Harshaw Creek fault. That's kind of the main one in yellow dashed. We don't know for sure that it cuts across the valley, but it seems likely that it's on the same lineament. The red lines are from the state database on that, Arizona Geologic Survey. We added more after closely inspecting the superficial geology maps that are available. I think there were at least 4. So you can see some light dashed yellow lines throughout. We made, for the modeling purposes, the initial assumption that all the faults act to impede flow across them. So you kind of expect water levels to rise up behind them and drop on the lower side. That may not necessarily be true in all cases, but that was an initial estimate.
Okay, thanks, Bob. This is satellite coverage of the 2014 vegetation types in the basin. And so this was the basis for the ET calculations in MIKESHE. This is from the 8-day MODIS satellite, LAI, leaf area index imagery. And then boundary conditions, generally no flow along the external boundaries of the watershed. And inside the watershed, one of the main boundary conditions is pumping. Unfortunately, without an AMA requiring everyone to report their pumping, we have essentially no pumping data. The only pumping data we were able to get was from the community water system in Patagonia. So for the rest of the wells shown here in green, we assumed pumping of 0.5 acre feet per year, knowing that that's inaccurate, but not having anything better to go by. This is a groundwater level map that was produced from water level data from DWR, GWSI, and Well 55 databases. Initially, every single water level taken from every single well shown here was just put in for a time averaged water level map. And so that starts the model. That's the initial condition. We recognize that that's not an actual condition, but it's a first cut. And the model equilibrates from that point forward. And then we use transient water level data. So the change in water levels with time, that information is used to calibrate the model. And general flow directions are shown here in the green arrows. This map shows depth to groundwater, where shallow is the warm orange and yellow colors, and deep are the blue colors. And if you recall, when we're talking about depth to bedrock, areas around Sonoyta Creek downstream of town and some areas of Harshaw had shallow bedrock. And you see that reflected here in shallow water levels as well. There are some areas with deeper water levels that are affected by geologic features like perhaps faulting and maybe pumping. But the important issue here is that shallow surface water really impedes infiltration and facilitates surface runoff. So preliminary model performance and calibration. This is simulated snowmelt on Mount Wrightson. We don't have a SNOTEL or any kind of snow course data from this site, but in a future higher level calibration effort, this would be calibrated using satellite information. This is simulated actual evapotranspiration, and that is produced on an hourly basis by MIKESHE, and we can compare it with actual ET values from external sources like EE flux and others. But this is to show that these higher precipitation areas of the basin generally produce more actual ET because of the precipitation increase, while the lower Central Valley part of the basin generally has lower actual ET, even though it's warmer.
Can I add one additional point, Laurel, that around the Patagonia area, where on the previous plot on groundwater depth, you showed it shallow, you can see a brighter green. So locally, that area does produce pretty high ET, as you would expect.
Right. So simulated discharge, meaning stream flows. This was a real challenge for us because there are no active gauging stations in this watershed. And I know Laura has talked to you about that before, but a continuous flow record would do wonders for any model in this basin. There was an old station maintained by USGS up until 1972, and I think they had some peak flow records up to 83. We actually used the data from this station, and I'll show you in a moment. And then we had the manual measurements shared by TNC from their preserve here. So that's it for stream flow data. Calibrating MIKESHE to stream flow requires some creativity in this case. So we had some other methods we'll talk to you about. But this is the first cut at simulated stream flow at the preserve downstream of town. You can see the manual measurements here in the dots and simulated curve in black. The manual measurements, I think that the curves are quite good in terms of match, but we don't have any information about peak flows because these manual measurements are only made by wading, and nobody wants to wade during a flood. So we really need more detail about those floods. And for that, the best we could do was going to this old USGS data and looking at some of the flood flow data points from the 60s and 70s, just to see if we were in the ballpark for simulated flood peaks. And it seems that we are sort of in the neighborhood. Preliminary simulated transient heads, these are not super accurate. You can see the observed values here and the simulated values in the solid lines. But there are many reasons in a preliminary calibration that these might not be accurate, including the 500-meter grid size, assumed pumping that we know is inaccurate, not capturing the local variations in geology that we know exist, but we don't necessarily have data for, and 500-meter grid doesn't necessarily capture. Maybe incorrect assumptions about all the faulting being impediments. Some may actually facilitate flow. A lot of the DWR measurements are either only very old or maybe only 2 points or just not a solid record. They might also be influenced by pumping, and we have to assume the screened interval on a lot of wells. We do not include upstream diversions and irrigation or legacy mine dewatering, or even any current dewatering that might be happening. So all those things could have an impact. And of course, that initial head condition is very approximate. So as you model farther out in time, this becomes less important. But the bottom line is, further calibration is required, as we know. This map shows simulated versus observed heads across the watershed. And basically the green triangles are pretty good, within 5 meters of observed levels. Blue is under simulated, orange and red are over simulated. There's 822 wells with multiple depths plotted here. And so for preliminary first cut, this we feel is reasonable. As I was saying, to calibrate to stream flows without stream gauging stations or any data really, we turn to another important data set from the Nature Conservancy that shows perennial flow status on some of the watershed tributaries and the main stem of the Sonoy Creek. These red areas are mapped as perennial flow. So we took that and looked at the MIKESHE models, places where MIKESHE model showed gaining streams, meaning groundwater is coming out to the surface and flowing down a channel. So like this light green here, and here, and all these light greens, those are essentially positive flow from the groundwater into a stream channel. And so you could equate that roughly with these perennial flow marks over here. They map pretty well. We feel pretty confident about that. And of course, the Sonoy Creek shows a lot of gaining here. There's another way to do it, which we haven't undertaken yet, but we could use isotopes, in particular tritium, to map the flow of precipitation and recharge into surface water bodies. So we're running low on time. I'm going to keep moving here. We have about 20 minutes by my clock here. The scenarios we ran were baseline conditions, so no mine dewatering from 2014 to 2020. And then we added the mine discharge at the second treatment plant over this same period. And then a third scenario was with just the dewatering. So no discharge here and no dewatering here. Our assumptions were that the flow from the treatment plant would be 4,500 GPM directly into Harshaw Creek. And we ran that for about 3.5 years and then turned it off for the next 3.5 years. We don't know how long it's going to take for the mine to dewater sufficiently. It could be more or less than this time. We just know that flow into the creek from the treatment plant is expected to diminish over time after the initial dewatering. And all of our modeling includes hourly distributed weather data and runoff. This is the initial simulated stream flow at the preserve downstream of town. You've seen this sort of annual cycle flows here and a couple of large peaks. And then when we add in the 4,500 GPM treatment plant, that is this curve here. 4,500 GPM is about the same as 10 CFS. We apply that throughout this 3.5 year period. and the simulated flows here are shown in blue. And so what you see is they're all bumped up. You know, the base flows are bumped up about 10 CFS, but actually the peak flows are bumped up more than 10 CFS. And we'll talk about that in a moment. Here, this graph is a little confusing, but it really shows that what I was just talking about, that the peak flows changed more than just by the 10 CFS that was added by the mine. So if the mine's dewatering flows of 10 CFS were the only change that were simulated in the model, all this yellow would just follow along this flat line of 10 CFS. That means that all the peak flows from the natural storm events would just be shifted up by that 10 CFS. But what we find is that the natural storm events suddenly produce much higher peak flows than just they're actually more than 10 CFS above the old peaks. In some cases, up to like 15 CFS or even more. So this is a function of that pre-wetted channel. Once flows sort of fill up that shallow alluvial channel and there's nowhere for rainfall to infiltrate in the alluvium, that water that falls on the watershed basically flows straight through Harshaw Creek, through town, and through the preserve. So we see flows at the preserve simulated as increasing by 200 to 600%, the peaks. And again, referring back to this presentation by South 32 in July, their area of impact for increasing groundwater levels as a result of Harshaw Creek discharge from the mine, they showed this area to be sort of oval with about a 3-mile width and ending right around the confluence with Sonoya Creek. What our modeling finds is that actually the impacts in this area are much narrower, much more confined to the few hundred feet around the channel, and that much of that water over time, after the initial wetting up of this creek system, over time, that flow is essentially conveyed straight through with very little dissipation here. The steady state analysis presented by South 32 in their APP was for basically a moment in time. It didn't account for any changing subsurface moisture or really any storm events. So they were looking at conditions at the time that they evaluated the stream channel. But we feel that it's very critical to consider what will happen with a natural storm regime superimposed on that. And this is another map showing the pollutant management area and the extent of flow. ERC estimated that there would be 132 GPM of flow at this point based on the discharge, from the discharge at the mine. Okay, Bob, do you want to go ahead and do this one? Or?
Sure. Yeah, I think this was just to point out that when we superimpose the MIKESHE model boundary on the left, that's a thick black line, with the groundwater model from, I guess, the South 32 presentation in July, with a purple line there, it includes a predicted extent of the drawdown. We don't know how long they've pumped that for, it doesn't say, or really even what depth. The figure on the right up at the top, there's some mine workings there and has a vertical axis. It sort of suggests that the mine workings might go down to 2,000 feet, but we don't know if that's sort of more of a conceptual cartoon diagram. But it does suggest that the dewatering looks like it'll go at least 2,000 feet. That's what we simulated in our dewatering, which is just a fairly simple quick evaluation, but it could be greater than that, maybe 3,000. And so our results have to be interpreted in that sense, that we only went down, made an assumption of 2,000 feet. We don't know how long that pumping goes on. But the red boundary there in the center is their drawdown extent. And then the green area is the groundwater mounding. We also don't know if that was run in the same model, but it seems like it's a groundwater model. And so we don't know how that would have included the surface flow that MIKESHE handles dynamically.
Okay, this is just the simulated MIKESHE groundwater decline in the vicinity of the mine as a result of the mine dewatering. And, you know, based on many assumptions, as Bob just laid out, you can see the blocks here reflect that 500-meter grid spacing. But generally, the outline of our dewatering cone depression sort of falls in line with that of South 32's, although ours is a little bit more aligned along Alum Gulch. Yeah, we just, without more detail, we can't really do a very accurate simulation of this. And this is just to show, sorry, go ahead.
Sorry, Laurel, can I just add one other point on this about the springs that occur kind of within the footprint that might be impacted? We actually don't know if those are connected to the groundwater system. They could be shallow, but it seems like they could also be very connected. And so one would assume that depending on that dewatering, the ones that occur within the red area would be impacted. The ones that don't wouldn't be.
This is just I'm quickly going to go through this, but with that dewatering profile here in red, you can just see all the legacy mines in the area, and many of them fall within that dewatering area. So the cone depression of the mine. So that's just another concern. Okay. Our main findings from this modeling exercise were that we kind of better understand the details of the system that influence flows. And we know that transient shallow groundwater and shallow bedrock and clay in the soil zone all exist in the system and are very important drivers of surface flow. Our MIKESHE results differ from the APP results that are presented from South 32. We show a range of impacts of flow through town and groundwater level increases. We derive our impacts from modeling the entire watershed, and we believe that that's very critical to understanding the impacts in town and below. We think that this fully integrated modeling tool is really, you just can't do without it because we have such a dynamically coupled groundwater and surface water system. So dynamic, very fast, very quick and transient. We need to be able to model continuous response to each storm event, and we need flows. And without stream gauges in the watershed, there's no other way to really simulate flows down these channels under normal and maybe not normal climate conditions. Regarding the discharge at the treatment plant, we feel, based on our simulations, we conclude that the proposed treatment plant discharge is likely to quickly saturate and fill the alluvial aquifer along Harshaw Creek, and that it will flow through town and the preserve after the initial wetting period. It'll increase peak flows downstream on Harshaw and Sonoyta Creek through town and the preserve by more than just the amount of the treated water itself. It'll facilitate transport of any contaminants that come in from above the treatment plant to downstream areas. And this is important because of the legacy mines. So if there's something happening in Harshaw Creek in the impaired area above this treatment plant, those contaminants will more easily make their way downstream if the channel is flowing constantly. And we know that this discharge will raise groundwater levels both along Harshaw and Sonoyta Creeks. From mine dewatering simulations, we believe that the lateral extent of the dewatering is similar to that presented by South 32, although our model is uncalibrated. We found that the dewatering rate is actually much lower than what South 32 presented. We don't have the details of the local geology or the dewatering simulations that the mine did. We found that there are numerous springs within the drawdown footprint. We don't know how much they might be affected because we don't have much detail on them. And we know that faults likely influence drawdown and infiltration and could translate drawdown to Sonoyta Creek. We still have some questions, of course. Will the mine dewatering and treatment address water quality at the intercepted legacy mines inside and outside of the mine footprint? How will post-mining water level recovery and discontinuation of that discharge affect baseline conditions along Harshaw and Sonoyta Creeks? If the mine is continuing to operate for 30 years and then everything is turned off, that cone of depression at the mine will gradually equilibrate, and the gradient of flows from surrounding areas will start to turn toward that area. So that's a long-term question. What will be the long-term post-mining water quality impacts? We found some basic things that we believe are missing from the South 32 analysis of the treatment plant discharges. First of all, we believe that there's shallow bedrock constraints to infiltration in the channel. We don't believe that was covered in their analysis. We feel that, understanding the depth and nature of the low permeability bedrock in the channel is critical. And we really think there should be a geologic model built for the entire basin, really, based on boreholes and geophysical surveys. We don't feel that lithological variations above bedrock in that soil zone really captured the extent and nature of the clay layers there. We reviewed a lot of borehole logs, not all of them, but we did find many that show notable clay layers. And again, there's a need for really understanding the geology here. The dynamic groundwater table beneath Harshaw and Sonoyta Creeks is not really considered in the steady state analysis that South 32 presented. So we feel that because of the already shallow water table, we really need to understand that groundwater surface water interaction and in a normal storm event profile and in possibly other conditions. Sonoyta Creek inflows above Harshaw Creek are completely avoided and not presented at all in their analysis because their model didn't cover that area. And without gauge data, you have to really rely on the techniques that we described with the integrated model. And you can't do it without modeling the entire catchment upstream of that confluence. And we know that the heavy clays in that area could be a real concern for flooding in town. The distribution and dynamics of soil moisture also were not really considered in their steady state analysis. You have to consider that, wetting up the channel with mine dewatering water will change the condition that monsoons, storm events will encounter when they hit the ground. So when rain falls on a wet soil and that groundwater is very close to the surface, you're going to quickly fill up the alluvium and generate flow downstream. Storm runoffs upstream of the treatment plant on Harshaw were not considered as well. They were considered only in terms of flow into the mine footprint, but we know that there are legacy mines upstream of the discharge point and downstream that both need to be considered, again, within a model of the entire catchment. We have a long list of data gaps. That's no surprise here. Maybe top of the list is topography. We'd like to have a much more refined picture of the shape and nature of the landscape. More detailed characterization of the alluvial aquifer along Harshaw. We don't have really good depth and width information of the alluvium there. Map legacy mine footprints, the adits, tunnels, shafts, etc. That'd be very important for understanding the groundwater system over time during and after mining. And details of mine water use throughout the 30-year predicted mine life of the Hermosa project. A geologic model of the whole basin. continuous water level groundwater level monitoring in wells along Harshaw and Sonoyta creeks and in the upland areas, and stream flow, obviously, we've covered that, but we really like to have much more detailed measurements of stream flow above and below the treatment plant on Harshaw, as well as above and below town on Sonoyta Creek. TNC is excellent at doing wet dry mapping. That kind of information could be super helpful in calibrating a watershed model here. High resolution meteorological data would be helpful for refining some of the data that we get from the satellite-based tools. Pumping and diversion data, of course, are always lacking and difficult to estimate, but that would be a big help. And then we believe that more frequent and informed water quality monitoring at the treatment plant and the mine's point of compliances will be really important, because we know that runoff events are going to be happening, and they're not going to be happening just at quarterly intervals, which is the proposed monitoring cycle for water quality at the treatment plant. We believe that there should be some kind of a smart system where, you know, when there's a runoff event predicted or noticed, then water quality should be monitored right away. And then hydraulic testing, any aquifer testing or long-term dewatering pumping that's happening in the mining area would be helpful to understand. Our recommendations are that we conduct a more rigorous analysis of this project, this problem, using an integrated code like MIKESHE, so that we can really capture the dynamics of the groundwater and surface water system. We want to make sure that the entire system is modeled. Everything above Patagonia Lake really needs to be incorporated. We need more data collection for at least a year. Really, surface water and water levels, groundwater levels would be very important. We need a 3D geologic model, and we need to improve the calibration for the last 20 years so that we can reproduce complete storm hydrographs, average and transient well water levels, and actual evapotranspiration. After the regional model is well calibrated, there could be a local scale model, like on the scale of 40 meters in the area of interest, to really examine with detail the dewatering and the discharge into Harshaw Creek together, as well as any other mining alternatives that might exist. And then the formal uncertainty analysis should be done to assess the range of impacts that might occur and identify the worst case for future planning. And then peer review of the work would be ideal, and to ensure buy-in from all interested parties. There are other applications of integrated models, and we feel this one could be used for lots of things, including assessments of erosion impacts from the additional flow to Harshaw and Sonoyta Creek, spring hydrology, ET changes, meaning resulting from increased flows along the creeks, changes in wetted areas in the channels and vegetation changes, long-term water quality changes, and climate change. And then mitigations. The model is capable of simulating a variety of types of mitigations that might be considered. So, for example, maybe a reservoir on some tributary upstream of town to temporarily store the treatment plant discharge and meter it out slowly so that the town can utilize that water but not be inundated. That would help minimize flooding and help the town maintain its supply of water in the face of climate change and drought and pumping. Enhance wetland habitat. That could be done with the wetland shoreline areas around the reservoir. Could also include a passive wetland treatment system to mitigate long-term water quality impacts to Harshaw and Sonoyta creeks. And also sorry, that's my timer. I guess I'm up. Also enhance habitat in the area. And then erosion control structures like single rock dams or gabions, road swales, things to help control the discharge of sediment downstream. And there we go. Thank you so much for your time. And I guess, I don't know if there are time for questions, but I'll hand it back to you, Carolyn.
Thank you both, Laurel and Bob. This is very valuable information. As my t-shirt says, water matters more. It is our lifeblood, and we have to pay attention to what is proposed and to react, respond, and request accordingly. So thank you, Laurel and Bob. Patagonia Area Resource Alliance truly appreciated you were able to get on this as quickly as you were and to give us this level of thoroughness that you have so that this group can now talk about this information and what recommendation, if any, the Flood and Flow Committee would like to make to the town of Patagonia. We may or may not be able to do that today because this was a lot of information. And as you said at the very beginning, I am sure that there are a number of people who listen to this presentation who have a much higher level of comprehension and understanding of what you were saying than this individual did. I do want to open it for any questions that anyone might have. I think it is important to do that at this point in time. So please, do you have questions, anyone?
I have a question, Carolyn.
Go ahead, Michael.
Michael. Laura, is it possible to determine the static water level within the town limits? You know, right now our water level is approximately 25 feet. In some places near the treatment plant, it's at 7 feet. And these are under really dry conditions. When I was living in town, I had a dry well, you know, a dug well in my backyard. The water level was at 14 feet. That's getting closer towards the treatment plant. So if they start pumping all this water and then you reach a saturation point, I mean, at some point we would have a level within town that could be detrimental to the town structurally to certain buildings. If the water level rises to 10 feet, where some houses might be, is that a possibility? And can that be determined?
Certainly the model can predict that, yes. And how much of a risk it is, you know, I'm not equipped to answer that. Structural engineer,
yeah, no, I know.
But yeah, certainly that is part of the purpose of the model, is to evaluate those changes in groundwater and surface water that might occur or likely to occur under the conditions proposed by the mine. And you know, we would benefit from more information about those conditions that are proposed to be more accurate in our estimations. Bob, do you have anything to add to that?
Yeah, I would just say that's where that question definitely is directed at calibration level, and why, you know, what Laurel presented on further calibration is needed. What if you were getting down to the local detail of buildings in town? This is where having local LiDAR topography, better water level data from all the in-town information, looking more closely at the geology in town. You put that picture together, and then you actually can start to look at the finer details of water levels. But you would want to rely on a calibrated model to reproduce what you see and the changes over. That all goes towards collecting accurate water levels with time. So if I were to say what, you know, the town could do, collect groundwater level data. It's become quite cheap to collect those continuously with a transducer you put in the well. And if you can match those levels drawing down in the model, that gives you great confidence that you would be able to predict how that might change under a discharge like this WTP.
Yeah, we have all that data. You know, if you guys need it, you can get it from us. We've had well data going back, you know, probably years now.
Great.
Anyone else raise their hand?
Yeah, I have a question.
Go ahead, Chris.
Chris, did I understand from one of your graphs that the continuous flow level after discharge or during discharge is 5 times higher, about 5 times higher than it is today on average?
Not sure. Do you mean this predicted storm runoff?
No, the continuous flow that is caused by the discharge of the mine.
Oh, 10 CFS. What
Yeah.
is the base flow right now, Bob?
That was about 10 CFS at the preserve, and you're right. It was about 200 to 600% increase. So two to six times that background. But again, that includes these peak flows, which is sort of counterintuitive. We thought, well, if the water treatment plant discharge goes through town, you'd expect it to maybe go up by that amount. But what we saw is once you've saturated that, then you have the ability to increase a normal flood event peak flow above that, because the groundwater is already saturated along that Harshaw Sonoyta Creek, which is like a double factor working against that. And it's why we put this model together versus trying to do a simpler model.
And that saturation is almost instantaneous, right?
Pretty quick, because the shallow groundwater and the shallow clays that Laurel showed.
Right. All right. One other question, last one. The dewatering at the mine site is comes from quite deep, isn't it? Isn't that old water, as most people seem to say? And if it is, what is the chance on recharging that water in terms of the timeline?
Yeah, that's an excellent question. And that's one of the many things we haven't addressed yet, which is what happens when the mine closes down and stops dewatering. How long would it take for water to come back in, and where would that water come from?
Right.
We're not in a wet climate regime anymore. And you're right, that water is most likely old water, fairly old. I don't know how old, but without additional rainfall, then water will flow toward that depression, that cone of depression, from other areas in the groundwater system. And if some of those areas are connected to springs, then you could expect long-term impacts to springs.
Yeah. So you cannot say as soon as that water is discharged to a level of Sonoyta Creek, basically, it will not probably recharge the old water.
Right. I mean, it's possible that you know, Sonoyta Creek could even be impacted by the long-term refilling of that depression.
Okay, thank you.
Thank you, Chris.
Carolyn, one more quick question, if I
Okay,
might.
go ahead, Michael.
Laura, would you think it would be appropriate for us to ask ADEQ not to issue a discharge permit until all these questions are answered? Because they could have ramifications here at the town, and someone, you know, if a permit was issued and these things happen without an accurate analysis, I mean, someone would have to claim liability for those things. So, I mean, what would you think? Is that too much?
Well, I think it's important for the town to comment during the public comment process. And, you know, however you frame that is up to you. But we wanted to provide the information here to highlight some of the unanswered questions and real potential problems so that you could make an informed comment.
Thanks.
Thank you, Mike and Laurel. Any other questions? Val?
This may be a silly question, but I was specifically told at the open house that South 32 had last month that this project would increase the flow in some streams and could decrease the flow in other streams, and that as a result could decrease the acid drainage out of old mines, and that therefore it was a good thing. And what I'm gathering from what you're saying right now is that we don't have the data to evaluate that in any way, really. They will be impacted, but to say that some of the streams that are causing acid drainage would just dry up as a result of this seems like a somewhat seems like, you know, that may not be a correct assessment of what your model is telling us.
So yeah, I think I'll defer to Bob on some of this, but I think you're correct. We don't have the data to properly assess that at this time. And if it were true that dewatering was going to remove water from some exposed, oxidation problems in existing mines, that's great. But the question is then what after dewatering? What happens as well? So Bob, please continue.
Yeah, I would just add that, the dewatering removes a lot of water from storage in the ground, and that will take time depending on how long it was pumped and how much they pump out. And I would say within that mine footprint that was shown in the July presentation, it includes, for example, the problem mine site, the Lead Queen, is that the name of it? The one that the Forest Service was plugging and had some challenges with. So I could see that dewatering plume could actually draw that into it. And then when pumping starts, that could be smeared into what's elevating back up, potentially get into a stream, go down, and it's not being considered, but it probably ought to. That's why Laurel put in the data gaps. Old legacy mines ought to be known. I mean, I do a lot of work on sites that have dozens of old mines, and it's nice to know if they're old mines. You probably will never know that information, but it's worth considering in an evaluation post mining.
One more thought on that is that if you do dewater an old mine that's currently underwater, you expose it to the oxygen that will then can cause acidification of some of the minerals there. So once it does, then that can be a bigger problem than it started.
Thank you.
Thank you, Val, Laurel, and Bob. Any other questions? Okay, having paused. Oh, Dave just put his hand in there.
Yeah, I would just like to congratulate the two authors of this study. It's quite remarkable how far they've gone, and I'm very impressed. Thank you.
Thank you very much.
Thank you, Dave.